Hello, this is Harvinder Jabbal from BITS Pilani. This is the second series on designing and documenting the architecture. We have been looking at various views. So documenting is basically about creating module views, component and connector views, allocation views, and some views to depict quality. We sometimes document beyond views where we document the behavior of a system. We use various UML diagrams to indicate the behavior of a system. So let us basically look at the views that we are concerned about: module, component, connector, allocation, and quality. A few things to be understood about documentation. The documentation is as good as it is useful. If you do some very good work on documentation, but the team is not being able to use it, it doesn't provide information. Either they misunderstand it, or they do not understand it, or they do not know why you have written it, what it is about. Such a documentation is of no use. So you've got to keep in mind that documentation talks about user first. This chapter is outlined here for you. Since we say that it is so much to do with the user, the person you're writing the documentation for, we say that the users and audiences are important. We'll spend a little while on looking at the notation used, and then we will dwell for some time on the various types of views. We will visit views and understand what type of views are available and what they are about. Thereafter, we'll briefly look as to how we can choose the views we wish to use and how we can combine views. You may have such a large number of views leading to a lot of redundancy and could lead to contradictions, could lead to views that are superfluous. So we will combine views. And then we'll spend a little while on seeing how we can build a documentation package. A package would mean a complete unit, which we call documentation. How do we go about building it? We'll also spend some time on seeing how to document behavior. Document behavior is required when you're going into the system in a slightly more fine-grained way. The architect does have a lot to do with it. Very often, a lot of behavioral items are left to the designer. We'll get back and quickly make a mention of how quality attributes are brought out in documentation. As we have always discussed, that software architecture is all about quality attributes and how we deliver quality. So architecture is a tool to deliverance of quality. Something which we have to take particular note of in today's context is that an architect is basically trying to shoot a moving bird. By the time you got your target right, the bird has moved on. So with documentation, decisions and factors taken into account for developing an architecture keep changing. And in such a situation, we have to separate those items which are static from those which keep changing. So that has to be taken into account in documentation also, because by the time you would have written the documentation, it will not be reflecting the ground reality of what's going on. Agile environment in today's world cannot be ignored at any stage. Agility, as the word defines, requires a lot of flexibility, a lot of accommodation, getting things right first time, but getting the extent right as necessary at a point of time so that the work can take off. So we will go and understand what impact agile project development environments have on documentation, how they react to documentation, because you remember that agile does not give as much importance to documentation as it does to running systems. Yet, documentation being important, we have to understand its presence and its importance in the agile world. We'll quickly summarize this at the end and we get started. So let us look at the uses and audience for architecture documentation. What architecture documentation must do? It must be sufficiently transparent. It should be understood by new employees. It should, while leaving a lot of scope for change, it should be concrete. It should be able to serve the purpose for which it is meant. People should be able to start working based on the documentation. People should be able to discuss decisions based on the documentation. They should be able to analyze the need for the elements that have been decided upon. Now, documentation can both be prescriptive in that it sometimes tells people this is what you should do under so and so circumstances, like a doctor. It can also be descriptive. We know that something is true. We describe the truth to the audience. So it's a learning point for audience. They come to know as to why you're taking decisions that you're taking and what decisions are being taken. Now, we understand that for stakeholders, architectural document is essential. So we must understand the stakeholders, so that if we understand the stakeholders and we understand the purpose that will serve for them, why they want the documentation, we'll be able to give them the right quantum of right documentation. We will know what to capture and what to present. In summary, we say architecture serves the purpose of education, communication, and thinking. It helps you to analyze, to construct. It allows you to think about the system. It gives you a concrete written commitment on what the system intends to be, to do. So, educationally, new members join a team, they take a quick look at the documentation and they know exactly where the system is heading, what was intended. External analysts who come to study the system, before they start criticizing and making comments, they understand the context of the system. They come to know why the system is the way it is. If a new architect takes over, he comes to know the rationale based on which the previous people made their decisions. Once an architectural documentation is written, developers and other architects, they come to know the mind of the architect. The developers can make sure that the application reflects that mind, and other architects or future architects can take into account previous decisions while putting in new thought. And needless to say, you have to write down something, you have to model something to be able to think about it. And architecture gives that too. We move on to some notations, and very briefly we'll mention our notations. Notations, as in any documentation process, could be informal, semi-formal, and formal. Informal notations could be sketches. They could use natural language, could be in English. And these things are normally not meant for analyzing, they are just put down to get started. Basic line of communication, some rough sketches, general purpose diagrams would serve for informal. Semi-formal, you start using standard documentation. It does not go into too much of detail. Some rudimentary analysis is there. And you could use UML because UML does help you to communicate, though it may not be adequate for formal notations. Formal notations go in for ADLs. These are architecture descriptive languages. These could be used for formal analysis of both syntax and semantics. And They support automation tools for architecture. These are formal notations. They could belong to certain companies who are providing tools for architects. When you choose a notation, you have to make certain trade-offs. There's always a cost benefit involved. If you use a formal tool, you need time. You have to invest money. Can it be afforded? It definitely reduces ambiguity. It gives more opportunity for analysts. But then, can we afford it? Whereas informal notations, they could be easy to create, but no guarantees. You cannot catch the documentation as having said so and so because the language tends to be weak. Different notations could be used. UML has got its limitations. If you want to discuss schedulability, you want to know the timeliness of delivery, UML diagrams may not serve your purpose. You might like to go in for a scheduling chart. So you first figure out what you want to capture. What is the reason for having documentation? And then you can choose your notations and your representing languages. Let us now spend a little bit of time and look through the various views. So the next 14 slides will look at views. Views help us to divide and rule. We take the entire system and we try to divide it into units which could be interesting, could be manageable in proportion. We take up relevant views and we add documentation that applies to more than one view. So first we take up certain views, we understand them, and then we write notes which help us connect up the views and understand them in terms of each other. So the difficult part about views is which views to use. Because different views, they support different goals, they have different purposes. So you should not start off with a preconceived notice that certain views are good and certain are bad. It all depends what you expect from the documentation. And what you expect from the documentation depends on who are the stakeholders, what the stakeholders want from you. You will definitely bear in mind what will be the cost of the documentation, what benefit do we hope to derive. So a very expensive assignment on documenting an architecture may ultimately make it counterproductive in that your budget for architecture may exceed the budget even for developing the system. Let us take the first of the views, the module view. What is the module view about? The module view discusses modules, implementation units, cohesive sets of responsibilities. That's something we always talk about as designers. High cohesion, low coupling. You create modules, and these modules with a high cohesion, they are the elements of a module view. What type of relations do modules have with one another? Is a part of, depends on, is a. These are classic object-oriented terminology. So we see that this element or this module is a part of this element, a whole part type of a relationship. There is a dependency between elements. This element depends on that elements. The two elements will depend on each other. So you have to depict this type of dependencies in your module view. Generalization and specialization brings in the concept of polymorphism, brings in the concept of parent-child from the object-oriented world. So this type of relationships you try to create and you factorize, you move the common factors into a parent, a generalized unit, and specialized capabilities are put into separate modules. That way, when you break up your application into modules, it becomes much easier to focus on genuine concerns. When we have understood the elements and the relations, let's look at constraints and the usages. Module views sometimes present a topological constraint. How do we draw them on a flat piece of paper? After all, we don't work in 3 dimensions, not 4 dimensions. So sometimes when you start connecting modules to each other, it can pose a constraint in even putting down on a two-dimensional paper. Yet, we overcome it. Sometimes we make submodules, we go at various levels of granularity, we try to show certain aspects of the views in separate units after having broken it up. What use is it? Well, when you want to construct code, you can divide your job between modules. Construction of the code, the jobs can be delegated by modules. You know the impact of individual modules on the overall system. You can plan incremental developments in the sense that you may plan major modules first and leave out certain modules for development later. You can create stubs and test your modules using stubs and proceed. You can trace from one element to other as to how data moves. You can communicate the functionality of a system by dividing into elements. So the moment you divide into elements, your understanding of the system improves. You can assign work, you can implement schedules, you can budget each module much better. And all in all, it helps you to document or structure the information about your application and helps you to manage your system. From here, we have seen that almost any documentation will definitely have at least one module view, because most developers start off by taking the application, breaking it apart into units, and we call this the module view. What about the component and connector view? You have the elements and the relationships between the elements. The elements of a component connector view are obviously the components and the connectors. The principal processing units are the components, and the pathways for interaction between the components are called the connectors. Now, what relations do these components and connections have to each other? Components are called component ports, are associated with connector rules. So you have component ports. Each component has got ports, and these ports have got connector rules so that these ports can connect onto connectors. So you have to design your ports to be able to use connectors. They have to be compatible to the connectors. And then you have the interface delegation. In many situations, ports are associated to some internal sub-architecture. You have an architecture internally. You have a serial port. You've got some internal architecture which delivers the serial signal. So that's an internal architecture. So you will have, this becomes an interface delegation. The port is an interface delegation. It's a serial port. So it will connect to various connectors. What type of connectors? Serial connectors, which in turn will connect to the other serial ports from other components. So they are the type of relations that these elements have with one another. Constraints, obviously, since you have only components and connectors, that itself is a constraint. Components can only be connected with a connector and the correct connector. If you don't have the correct connector, you can't connect. And the connectors will only work with components which are the ports designed for it. So compatibility becomes an important factor. There's got to be a match between the ports and the roles. Interface delegates can only be defined between two compatible ports. If you don't have compatible ports, you can't have an interface delegate. Now, another thing is connectors cannot exist in isolation, nor can your components exist in isolation. They can only exist with other connections, can only exist with other components, and components can only exist with other connectors. What is the use? It gives a very clear idea of how the system works. You have your components, they do this. These are connectors with whom you connect. They help you they give you a guide for development. You know what's the structure, you know what components to develop, what are the connectors you have to have in mind. And it gives you a very good sense of the runtime behavior. Unlike your module view, which was more of a static structure. And it also helps you to start reasoning about quality attributes like performance, availability. So you come to know where the bottlenecks in the system. You know what are the performance bottlenecks likely to be, because you know which components take what type of resource. So component connector is a beautiful view on these fronts. Now, how do we go around documenting components and characters? UML is a nice way to do it. There are some UML diagrams shown here. We have some UML diagrams shown over here. And I will take you to a website, and you should spend some time on this, where you can look up some theory on UML. We are not going to spend time in class understanding UML, but you need to understand. There are two figures here, UML1 and UML2, and this site is agilemodeling.com. It's a useful site to spend some time on. At present, we focus here. Please take particular note that this ball and this socket. This socket provides an output for an input. So these are worth taking note of. This is the UML1 notation, which brings out the port very clearly. You got your interface. See, notice the circles and notice this output socket. So this is an output. A ball will fit into the socket. The ball will take the input. So they have to be compatible. And here you look how difficult it can become sometimes topologically to be able to present it. The arrows start crisscrossing. So it's a nice little article here, and it would be a good idea for you to spend some time reading through it. Notations. We said that UML connectors are not rich enough to represent CNC views. They cannot show you substructures, attributes, behavior descriptions. You can use simple CNC connectors using UML connector lines, and many commonly used CNC connectors, they will be able to present a good bit of information, and at least at a semi-formal level, you will be able to communicate a good bit about your CNC views using UML. Connector rules again, though they cannot be very clearly represented, because UML does not allow you to include influences, you can definitely identify rules and then you can document them elsewhere. You can write a documentation indicating what rules. You can use annotations. You can use UML, and then how does UML allow annotations? Put a small circle, put a line, and put a small tagged box where you can write the description. So you can use UML diagrams with annotations to make a fairly powerful presentation. So that is one way you can present CNC views fairly powerfully. Now, the next view is allocation view. It's a dynamic view. It talks about software element and the environment. It gives you the element properties that are required from the environment, and it also provides information about the properties that are provided to the software by the environment. The relations that are presented are allocated to. Allocated to, the moment we talk about allocated to, we are talking about resources. Resources could be RAM, resources could be hard disk space, resources could be manpower, resources could be processing time. Any particular allocation is a part of allocation view. Now, the constraints, there's a variation, and there will be constraints depending on what you're trying to present in allocation. There would be limitation, but still, its allocation is a very useful view. It gives you reasoning about performance, availability, security, safety. It has a huge impact on quality attributes. It tells you distribution of development, how will you distribute your development work, how you allocate work to teams. That's also an allocation view. Reasoning about concurrent access to versions, reasoning about the form and mechanism for installing the system. Everything that takes the system into working is covered in the allocation view. Then we talk about quality views. So this is an additional view over and above the three basic views we talked about: module, CNC, and allocation view. Now, a quality view can be tailored for specific stakeholders, stakeholders to address specific concerns of stakeholders, because different stakeholders have different quality concerns. So you would vary your quality views according to the stakeholders. Now, you can create quality views by extracting relevant pieces from structural views and packaging them together to demonstrate how certain quality attributes are being handled by various components of your system. Let us take some examples of quality views. So first we talk about security view. Here we see components that have a role or responsibility concerning security. We see how the components handling security communicate with one another. For security purposes, you may have to maintain certain repositories. You might have to maintain the IPs, you might have to maintain the machine IDs, you might have to maintain certain information about attempts to log in, failed attempts. All this information needs to be presented in the security view. It also tells how security measures, could be physical security, lock and key, are implemented in the system's physical environment. There could be a behavior aspect. We also said that we document behavior to document architecture. In the behavior part, we talk about security protocols. How do you change password? How do you deliver password? How do you allow access? How do you identify, authenticate a user? What are the systems for authorization? So the entire security protocol, it could be explained how humans interact with these elements. This would be a part of the behavior. Behavior could capture response to threats and vulnerabilities. If there are 3 repeated attempts with wrong password, it may not allow access for next 10 minutes. May send an SMS to the user on his registered telephone number. So it captures behavior. So these views which present everything to do with security, we'll call it a security view. Next in line, let's talk about communication view. Communication view has got to do with communication. When do systems need to have a lot of communication? When they're dispersed, heterogeneous systems, globally dispersed, internationalization could be a factor. How the components and connectors communicate, what type of channels could be used by these connectors, what type of networks are used, quality of service parameters, how concurrency is implemented in communication, what type of communication, synchronous, asynchronous. Performance comes to play, reliability comes to play. You may have deadlocks, race conditions. You may have need to wait for each other, locking of resources. Now, all this type of behavior may impact dynamic allocation of bandwidth, the reservation of the resources, IRCTC being a case in point. Students could try to look up how very good communication has been achieved over the last few years by IRCTC to achieve better performance, better reliability. So these type of things would be depicted in a communication view. We come to exception or error handling view. Now that we are looking at as a quality attribute. We want very good error handling or exception handling. So you might explain in the view what is the mechanism for error handling. Will there be a log maintained? Will there be a decision taken online? Would there be choices given to the user? What type of hot fixing methodologies would be built up? Whether after detecting, how will they be reported? How will you set it right? How will you make sure that error doesn't turn into a fault? How do you identify source of errors, plug them? And what arrangements do you make in the short run while there are errors? A reliability view may talk about replication, switchover. If there's a mirror, how do you switch over to a mirror with minimum intervention or minimum impact on the users? How timing issues are taken care of, how transaction integrity will be maintained on the event of switchover. So these type of things will be presented in a reliability view. Performance view could talk about system performance, how network traffic is to be handled, what type of latency, how these latencies be mentioned, what will be tolerated, how it is reported, and how decisions are taken to improve latency. So we basically taken a quick look. Now we come into choosing views. How do you choose a view? We've got 7 points listed here based on which an architect makes a decision as to what views to choose. What are the people? What type of skills do they have? So depending on the type of skills with the user segment, you will decide what type of views they should be provided. Are there any standards that the company has decided to comply, internal standards or external or international standards? So they will determine the type of views to be followed. Some companies may have a standard that if any system which will take more than 6 months of development time, we have to at least one module view, one CNC view, and one allocation view. What is the budget on hand? The views you do have to meet the budget in hand. Very often, we go in for a macro level view and we go horizontally. We don't go too deep vertically, so that at least you have an overall coverage of the architecture. So that would be directed by the budget. What's the schedule? If you don't have the time to have formal documentation of architecture, then you don't go in for formal documentation. What information is required by stakeholders will determine the type of views you will give, because different views are required for different type of requirements. Quality attribute drive. Again, certain quality attributes are reflected well in certain views, and even in the implementation of the views, you may be driven by the quality attribute requirements. Of course, the size of the overall system matters. The larger the overall project, more time you should put in for planning, it will pay rich dividend. A very casual and trivial project cannot justify any time on planning. So these would be the factors based on which you would choose your views. From here, we move on to combining views. Well, you have to combine a set of views to give something useful to your stakeholders. Any system would typically have at least a module view, even if there's nothing else. Anything a little more than trivial will definitely have a component and connector view also. Larger systems will definitely have at least one allocation view. So that's the order in which they move. And with very large systems, you will have a multiple of views. How do you go around choosing what views? The first thing you do is build a stakeholders and view table. On the left-hand side, one row for each stakeholders, and in the column, you have one row for each view that is candidate for you. What you initially considered based on your ADD, architectural driven development, you considered that certain views would be important to you based on the quality attributes that are of priority to you, and you put them down there. Having done that, you have got a matrix with a lot of blank space in between. So some views like decomposition, users view, work assignment view, they apply to every system. You might put it down. Views such as CNC, layered views, they may not apply to systems. So these would determine the columns. And in each matrix cell, you write down whether that view is not required at all, overview only, you need just an idea of that view, or moderate detail of that view, or high detail. If you find that a particular view is not seriously required, we will go around combining these views and or doing away with views altogether. So how will you go about combining views? CNC views, all runtime relationship among components and characters are taken care of. So you tend to combine them together to show your runtime behavior. Deployment views, they can show you SOA or communication process views. SOA view would tend to show you services. Communicating process shows you processes. If there's a commonality, you may decide to do without one of them. Now we come to decomposition views and any of the work assignment, implementation, usage or layer views. Now you will look at them and you'll decide which of them you would like to keep and which you'll do away based on the units of works, development or uses that you find out. And some of these you might do earlier, some of them you might decide, okay, we'll do it later. Let us have a fundamental view right in the beginning. At this stage, let's start prioritizing the views. In the early release, a decomposition view would be very useful. High-level decomposition, they're easy to design. You can take major design decisions. Your project can kick off. You may put together the appropriate teams right in the beginning. So in the beginning, you don't try to look at the needs of all the stakeholders. If you can get 80% of the information, which really requires 20% of the effort, Pareto's principle, it would normally be good enough. Now you can check with the stakeholders, like whether what you're giving them is adequate or not, because it's an agile process. You're constantly in touch with the stakeholders. So you can put these four together. Another thing to remember is you don't always have to complete one view before starting on another view. You can do a sketch of one view, give an idea, start developing another view. And sometimes users understand better if you've got 2-3 sketches views rather than a very detailed presentation on one particular view. At this stage, we look at building the documentation package. The documentation package consists of documentation about views and then some documentation which is beyond views. That means you talk about the interconnection of views, how they're used, where they fit in, but it's beyond the views. So how do we go about it? We start with a primary presentation. The primary presentation shows the elements and the relationship. So having done this, you're being able to convey certain information about the system in the vocabulary of a particular view. And primary presentation is often graphical because people tend to understand graphical sketches much better. It could be informal, and sometimes it is just textual. A small paragraph could be a table, it could be a list. So documenting a view could start with a primary presentation. So presentation becomes a part of the documentation. You could keep a recording of it. It gives people an information or the first view of the system. At this stage, you normally prepare an element catalog. So some of the elements will begin to emerge in the primary presentation. And once they emerge, you will have to explain what these elements are so that people begin to understand what you're coming up with. What are the elements you've been able to identify? So in doing that, you will normally indicate the properties of the elements, the relationship between these elements and the properties of the relations. Then what type of interface exists between these elements and how these elements behave. So you have the interface, you have the behavior, you have the relation between these elements, and you have the elements and their properties. This is what you try to put down from your basic preliminary presentation itself. Then you try to come up with a context diagram. You have to understand the system or a portion of the system in the context of the larger system or the environment. So, which gives you an idea of the scope of the view. Is the scope the entire system or part of the system? Which system it fits into? Now, the environment could be of various kinds. It could be a human environment, a computer system environment. It could be a part of a machine where it's an embedded system. It could be a part of a sensor, a control device, an office automation. Having given a context diagram, you have to think of a variability guide. Variability guide gives you the points of variations. This will become relevant later when we discuss as to how you handle documentation in a changing environment. You have to isolate points of variations in a system, the concept of protected variation in design. So you come to know that what are the variations possible, and we isolate the points of variations into a separate unit. This is a good design methodology. And then you explain the rationale behind your design as to what decisions you've taken and why you have taken the decisions that you have taken, in which case you will very clearly indicate the goals that you have tried to address, why the choice of patterns was made, and what quality attributes it is expected to deliver. So other people looking at the architecture at least understand the rationale behind your having taken the decision. A typical view would have a template like that. You have a primary presentation followed up with a catalog indicating the elements, their properties, relations, and the properties of the relationship, the types of interfaces, and the behavior. You draw a context diagram, give a variability guide, and explain the rationale. So these 5 sections would be an important part of any view template. Let us move beyond views and see what information is to be documented beyond views. Control information. You prepare a list, issuing organization, the current version number, the date of issue and the status, a change history, procedure for submitting change requests to the documentation. All this is written down, and usually this is put up as a front matter. And then we start. First thing we present is a documentation roadmap. It tells the reader what information to find in the documentation and where to find it. So typical outline would be scope and summary, how the documentation is organized, a view overview of the views, which tells what views have been included in the documentation. You will indicate over there the names of the views, the description of the view elements, the relation types and properties, and a description of the language, modeling techniques, analytical methods used in constructing the views. Thereafter, it will indicate to the stakeholders how the author of the documentation perceived that the stakeholders will use the documentation. It will indicate what concerns of the stakeholders this documentation will address. So the stakeholder knows, okay, he has done this documentation to address so-and-so concern of mine. It should include scenarios. The way we have studied scenarios, a maintainer wishes to know the units of software that are likely to be changed by a proposed modification, and then how the change will be attended. Any compliances that you are addressing, if there are some international standards or compliances that are being maintained in the documentation, it could be mentioned here. Then explain the standard organization you use to document the view. If there's a standard organization, if you want to write your own organization, you could use it, or you could follow what is suggested by the author of our book here. And that's how you can organize your documentation. A short prose explaining the system overview is always good in a documentation. It gives an idea to the user as to what the system is about and what context it has been brought up. It gives the user a preview of what an operation document may look like later on. So this type of a system overview can be very useful as a part of an architectural documentation. The next thing that documentation may need to cover beyond the views is a mapping between views. Now these views, they relate to each other. There's an association between views. Sometimes you can draw a table And in a table, you can show the corresponding elements of two different views. You can put a component and connector view and a module view, and then you can indicate which element in the component and connector view is implemented by what unit in the module view, or the other way around. That which unit in the module view implements which unit in the component and connector view. Sometimes there is a decomposition. So you could indicate what elements have been decomposed into what elements, a mapping of decomposition as to how these elements are relating to one another. A rationale behind selecting the views could be in good place. So why you have got these views? Why did you not manage with just one or two views? Why were these additional views necessary? These type of decisions could be documented. And then you can have a directory giving an index of terms, a glossary, an acronym list. These could be points beyond views in a documentation. Now we come to documenting behavior, which has not been covered under the classic documentation we talk about under software architecture. We now bring in the concept of documenting behavior, a subject which basically moves from architecture to design. More concern of the designer, but architects like to give some preliminary idea of behavior to the designers. Now, we have most of you students or all of you students would have studied documentation on behavior in object-oriented analysis and design. So we will not go through that in detail in the chapters here, but we'll mention them here and provide an adequate motivation for you to review your course on object-oriented analysis and design so that you are in a position to face an examination where you may be required to document certain behavior to depict certain types of software architecture. Now, behavioral documents, it complements the views. The views on their own may not be able to speak for themselves. Behavior documentation helps them to speak up. It indicates the behavior. It will give us information about deadlocks, time desired, memory usage. So this type of information will come out of behavioral documentation. Now, basically, any document which shows behavior uses a trace-oriented language. It shows you a sequence of activities. It shows you interaction between elements. And it shows you the way the structural elements of a system talk to one another. Examples, and all of which you have studied in the past, include use case diagram, use case text, sequence diagram, communication diagram, activity diagram, message sequence diagram, timing diagrams, and state diagrams, business process execution languages would be a part of this. And with that, I will quickly show you the next few slides without trying to explain their content. Here is the use case diagram. Enough time has been spent discussing these in other courses. Use case description. You're familiar with informal, semi-formal, and formal presentation. The full dress use case text is not lost to you. Sequence diagrams. You've drawn a lot of sequence diagrams for the point of sale examples. You've been working on the library example, and while preparing for examinations, know not what examples, including the ATM, would have been done by you. But please study this with a magnifying glass and revise your knowledge on sequence diagrams. Communication diagrams, close sister of the sequence diagrams. There are certain things better told by the sequence diagram, and some other things that are better told by the communication diagram. Sequence diagram has got limitations that it has to be ordered in a certain way. Communication diagrams has a lot of flexibility, but doesn't indicate the timeline as clearly as a sequence diagram does. Rather, timeline is brought out very clearly. The numbering methodology in a communication diagram had a lot of importance, and has been the cause of lots of students losing lots of marks in examinations. And professionally, if you don't number these communication elements properly, it does not tell the complete story. Activity diagrams, the familiar swim lane diagrams. You have the swim lanes running horizontal over here, various departments of various activity segments, and the various types of connectors in an activity diagram are all too familiar to you. Now, comprehensive languages, various models to complete behavior of structural elements are being presented. You can have a state machine language which presents the state machine diagrams giving the states of the system. Now you look at a typical example of state machine, you study it, gives you a lot of information about the system and how the elements would be communicating or controlling each other. We have a more complex example of state machine diagram with sub-elements, which brings out things very, very clearly for you. With that, we move on to documenting quality attributes. Quality attributes have to show up in documentation because that is the primary item being thought of by the architect. He is trying to address architecturally significant quality requirements. So these quality requirements, they get documented in your architectural document. Now, where do they appear? How do they show their head? You show certain rationales of choice of design approach. You may be showing certain discussions in your documentation as to why you've made certain trade-offs, why you made certain choices. And when you make these choices, you'll definitely be talking about quality attributes because this is what we wanted to achieve, this is what we did. Other thing is that architects, they work on attribute-driven requirements. Quality attributes are specified to an architect that this is what you need to deliver. They are defined in terms of interface and they are recorded as properties. And these elements are supposed to exhibit the properties because whatever quality requirement that was required, an architect will try to implement it through certain elements. Those elements will have a role which will try to achieve those quality attributes, and hence in the choice of elements you will see an underwritten quality requirement. Quality attributes, they impact the language. When somebody talks about a requirement in architecture and somebody who understands architecture well, he will be using the language of quality. At every point, he will say that he'll be looking for so-and-so type of quality architectural elements and which focus on quality attributes. He will be looking for reliability. He'll be looking for security. And in choice of elements, these things get brought up. The fourth item is when you start mapping requirement and then you start checking whether the requirements have been met or not by your candidate architectures or your hypothesis of architecture. These requirements are always signified in terms of quality attribute requirements. And when you talk about achieving your requirements, you are achieving your quality attribute requirements. Lastly, there are stakeholders behind quality attribute requirements. When the stakeholders are told the roadmap and the stakeholders told where to find their requirements being executed in the documentation, you'll end up telling the stakeholders that your requirements have been met. And behind every quality attribute requirement, there are stakeholders, and stakeholders will be looking for an architecture that will satisfy their quality attribute requirements. So, in finding the constituency of stakeholders who look for certain satisfaction, we will be mentioning quality. So, quality is pervasive right across documentation, and this is what we look for in architecture, so it definitely has to deliver. Next thing of concern is that architecture that changes faster than then you can document them. You finish documenting the architecture, and before you finish documenting, architecture itself changes. We normally say of such architectures that it's got a high frequency release and deployment cycle. Even in a high frequency release and documentation cycle, there is something continuous about it. There are certain aspects that don't change. All versions cater to that. So when you do documentation, you separate out the commonalities, the basic theme that runs behind the system. The major systems, software like WhatsApp, Facebook, they're continuously reinventing themselves, but they don't lose the basic character. The basic character could be documented, and the variability could be separately documented. That these are the points of variation, and the current focus on variations and the morals behind or the objectives behind the variations could be brought out. And that would be the purpose of the architecture, to let the community know as to the areas in which variations are being planned. Let's move on from there to an agile development environment. So in an agile environment, we develop a template, but we don't try to complete a documentation. You may do documentation in a scattered way based on the focus of the agile team. Typically, in an agile requirement, you'll go horizontal first. You'll be looking at rough overviews. You may leave out certain parts of documentation altogether, and you may leave out fine graining to a later stage. Certain parts which are not applicable for now, you'll completely strike out. And even the parts of the documentation you would do, or the type of parts of the architecture you'll formalize and finalize, may be done at a very coarse level initially. You don't bother about creating a complete fine-grained documentation, but you are concerned about having a fixed template and completing on the template and letting everybody know how the template is emerging, and making sure that the high-risk areas and the areas which are of concern architecturally are taken up first. And it's apparent to anybody looking at the entire system that the entire system is documented and it has got a particular direction in which it's going to be moving. So agile teams typically have a discussion board, and very often the documentation which is changing is put up on the board itself. So you don't have time to publish and release and have it put up in various places, but the team knows exactly where they are going and which are the areas in which they allow variation, where they don't. So this is how an agile team would typically work. A lot of flexibility, yet the idea being to get good products out in the shortest possible time. With that, we have given an overview on documentation. Now let's summarize it very quickly. So what you write depends on who you write it for and what purpose it is to serve. It can be a means of communication. It can be a channel for managing people. It could be a channel for teaching people. So architectural document could be used for teaching, for communicating to people, or for management purposes. Now, architecture, being very complex, is represented in a number of views, and there's some documentation we do beyond views. We have to make choice of the notations and then find out a minimal set of views that will probably cover enough and uncover enough. So you basically start off with the structure, and if the structure is properly covered, there's a lot done. And thereafter, after developing your structure, you gradually add on more and more information about the views, and the document keeps evolving itself. So documentation could be an evolving document, and for an architect, architecture may not all come as one big bang. It could gradually develop out of the needs, and particularly in today's case, in an agile environment, depending on the focus of design and development and the priorities set for development, your architecture would evolve. With that, we complete our session on documentation. Thank you very much. There are some credits to be given to the people who have provided the knowledge behind the presentation. So please read the book and do follow it. Thank you very much.